Hello everyone, welcome to Regina Astronomia. I'm your host Regina Kim and I'll be taking you on the exploration of colors and lights.
Please for mankind.
Over this video, we will explore spectrometry, wavelengths, black body, and even dark matter. But before we step into stellar spectra, let's take a step back. I want to talk about
Wien's law. Wien's displacement law gives the relationship between the peak wavelength, lambda max, and the surface temperature, T, of the star measured in Kelvin. It states that lambda max times T equals to 2.9 times 10 to the power of negative 3 meters Kelvin. And the color of a star depends on its surface temperature, as with any hot radiating object. Most stars look colorless or white because the human eye's color receptors need light to be brighter than a threshold value before they work. Thus, by measuring the intensity of the starlight at different wavelengths and plotting them on the spectrum graph, we find the wavelength which corresponds to a specific color. A cooler star will look red, while a hotter star will look blue. Ironic, isn't it? By studying the absorption spectrum of light passing through nebula, proportion of 74% of hydrogen-1 and 25% of helium-4 by mass, along with hydrogen-2, helium-3, and lithium can be seen. This proportion can be observed in the initial state of the universe as well. And the theories of nuclear and particle physics predict that this mix would emerge from the first 20 minutes of the Big Bang. But why do stars even emit light? When electron, which is non-baryonic matter, receives energy, absorbing photon, it gets excited and jumps up an energy level. And this process constantly happens in stars due to their high temperatures. And that electron emits a photon as it comes back to a normal state. Therefore, atoms emit and absorb specific wavelengths that are characteristic of the element. The light from a star has an atomic absorption spectrum, which is basically dark lines on a rainbow. These absorption lines are a crucial source of information about the star. They tell us which elements are present in the cooler atmosphere of the star where the photons are absorbed. Furthermore, the pattern of the lines are Doppler shifted depending on the wavelengths, either they are shorter or longer, making it possible for us to determine the star's velocity relative to the Earth, which is how fast the star is moving towards or away from the Earth. Stars also follow the Stefan-Boltzmann law that gives the total power of the radiated energy as a function of the Kelvin temperature, T, and the surface area of the body, A, stated as P equals sigma A T to the power of 4, where sigma is the Stefan-Boltzmann constant. This radiated power is equivalent to the luminosity of the star. There are stars that change luminosity. Variable stars, or simply variables, are stars whose luminosity changes with time. Cataclysmic variables, such as supernovae, produce sudden flares at unpredictable time. However, periodic variables change their brightness predictably. By observing the period of a Cepheid light curve, which is a relatively simple observation, it is possible to obtain the star's peak luminosity. This luminosity period relationship is known to be directly proportional. By measuring the brightness directly, it is then possible to determine the distance to the star. An object whose luminosity can be determined indirectly and thus can be used as a distance marker is called a standard candle by astronomers. Stars may be classified according to the characteristics of the absorption lines in their spectra. This spectral class can be shown to be related to the surface temperature of the star, providing another way to get the information about the surface temperature of a star. Stars radiate like a black body due to their very high temperatures. A black body refers to a surface that absorbs all the incident radiation and would therefore look black when cold. Black bodies also emit radiation in a spectrum that is wholly dependent on their temperature with peak intensity at a wavelength given by Wien's law. Wien's displacement law states that for a black body, the wavelength of peak radiation emission, lambda max, is related to the temperature T of the black body. It states that lambda max equals to 2.898 times 10 to the power of negative 3 meter kelvins over T. But objects are never true black bodies. Similarly, dark matter is postulated to exist but has not yet been directly detected. Dark matter does not emit or interact strongly with light. However, dark matter plays a crucial role in cosmological models that account for the evolution and existence of large-scale structure in the universe. The current best estimate is that in the universe as a whole, there is more than 5 times dark matter than luminous matter. Because dark matter does not absorb, reflect, or emit light, we do not know what it is made out of.
All the information we have about the universe comes in the form of the light. Even humans, you emit light. Our eyes just can't see it.